hard time finding the quiz. I accidentally did not add it to the home page. It was on the quiz tab, so it was there. But if in case you guys need some more time to take it, the quiz for yesterday will be up till midnight tonight. Today's quiz will also be up late again. So that shouldn't happen going forward. This week just got a little crazy. So expect that quiz out sometime, hopefully tomorrow morning, pretty early. And what else? Homework 1's due tomorrow at midnight. Tomorrow's Friday. So tomorrow at midnight. If you have questions about that, please attend office hours. I think are there any tomorrow? I don't even know if there are any tomorrow. So then post on Piazza and we'll get on that.
When will your regular office hours be?
I've still got to schedule them. I was supposed to be on jury duty this week, so I needed to put it off a week. But expect those to be posted sometime next week. I'll only have 1 hour a week probably scheduled. We have, I think, 10 hours, or it's not quite 10 hours with the CA because she splits it between Piazza and office hours, but a lot of hours with the TA and CA. So please try and attend those if you have like general kind of course related questions. Happy to answer those in my office hours, but logistics stuff will take precedent. But yeah, expect me to post a more solid kind of scheduled time next week. Anything else from mine? Expect homework 2 to go out sometime tomorrow morning. That'll be due sometime early next week. I need to take a look and see how long it is again. I don't quite remember. I think it'll probably be due Wednesday night. Could be Tuesday though. I'm not sure yet. Other stuff on my end. That's about all I can think of. I think there was something else, but I tend to say that when I'm grasping for something to say. So, yeah, that's about all I can think of. If somebody thinks of something that I forgot to do, please let me know. I don't think I posted yesterday's class notes yet. Expect those when I post today's lecture tomorrow morning sometime. And I think that's about it. Any questions before we get started, though, on subject matter, logistics, anything like that? Cool. Well, let's jump into it. So yesterday we finished off by looking at a couple functions that had a pattern in them. They were similar in certain ways. And this was this add 5 and this all not function. So add 5 took a list of numbers and adds 5 to every element in that list. And all not does something similar. It takes every element of a list of Booleans and applies the negation function to it, the not function. And so kind of a question we asked yesterday, or I don't know if I asked this explicitly, but what were the similarities and differences between these two functions? Well, other than the names, right? The naming is of course different. So for instance, the recursive call is different, but it's not really different. It's really the same thing. It's just because we had different names there. So those are similarities. The only real difference was this part I highlighted in white there, is the actual function we're applying is different, right? Otherwise, we're just kind of what we would say mapping through a list. And so then we asked, okay, well, can we write a function that does this? Can we abstract to this? And so we got on this, and it's a function called map. And map, as we said yesterday, has type. It takes a function from lowercase letters. Takes a function from A to B as an argument. I need to be consistent with my lettering. If I ever use uppercase letters as a type variable, let me know in a type, because I shouldn't do that. It's not allowed. Syntax we're teaching you. So function from A to B, we take a list of A, and then we return a list of B. And the big difference here is that this is taking a function as an argument. This is really where functional programming gets its name. It's because we treat functions as what we call first-class objects. They're a part of the programming language like everything else. They don't get any special treatment. They're part of the language itself. So we can use functions just like we would use a number. We can pass it as an argument to a function. We could put it inside a tuple or a pair of things, or we could put functions inside of a list if we wanted to. And map is an example of what we call, nope, wrong color. It's an example of a class of functions we call higher order functions. Now, what is a higher order function? Obviously, we haven't defined map yet. We'll get to that in a second, but I want to get through with this definition. A higher order function is a function that takes other functions as arguments. Okay, so fairly simple idea, at least the way I say it, but it has a lot of really big implications when we start to get into the weeds. But before we get to those implications and the details, let's try and define map best we can. So let's try and do this. So I'll come up here and pull this type signature. So we have step 1 is already done already. We did this yesterday. So we have map. Now let's define map. What cases should we have for map, do we think? What cases do we need for map?
Can you just repeat again yesterday where A and B were those functions?
Say that again?
Can you just repeat where we first started off with map yesterday was A and B were those functions?
So A and B are the types here of the function. So the function that we have is an input of type A and it outputs a B. That was what we finished on yesterday. And it's applying, the idea is that this argument is the function we're applying to everything in the list. Okay, so let's start out. Let's look at our other functions. So if this is supposed to abstract add 5 and all not, shouldn't the cases stay pretty similar? I think so. I think most of it should really stay similar to all not and add 5, right? So if we're trying to abstract, we want to look for what's similar and what's different. The stuff that's different, we want to try and abstract into a variable, okay? And the stuff that we want to stay the same, we can write out as part of the definition. So here, we'll have map of nil And we'll just leave that as nil. So if I'm trying to apply a function to every element in the list and I have an empty list, I better have an empty list when I'm done. That would be expected. Now, how about the cons case? This is the more interesting one. So, oh, and I need to be careful because it's not going to be map of nil anymore. It should be map of f and nil, where f is that function. So we need to be a little careful now because we have an extra argument. So how about map f of cons x and x's? What ought to go there? Any ideas? If you need a hint, you can look at the add 5 and all not functions. That'll give you a really good idea what should go there. Yeah, so I've got an answer from Lilith. And it's almost a correct one. 90% of it's correct. So she says cons of f of x. So applying that function to the element that we've just kind of peeled off. And then map, yeah, there you go, Lilith. And then map f of x's. Originally, Lilith had left off the x, but we need that f there to pass it back through. Yes. Yes. That's what the A to B is, right on. So F corresponds to, I'll highlight this, we'll use yellow for this. That's too big. F corresponds to this A to B function. So whatever F is, it has type A to B. I don't really care what precisely it is, right? Because we're trying to abstract here. We're saying, just give me a function. As long as the function is consistent with what's in the list, I can use this function. Okay. So now we've written the function. Actually, I should ask any questions about the function first. Is this like super confusing to anyone? We'll see some examples, especially with applying it, because we've written this, we've abstracted it, but what's the use of a function if we're not going to use it, right? So now my question for you guys is, can we redefine all not and add 5 using the map function? Okay, so let's start with add 5. Oh, that's a highlighter. So add 5 is a function that takes a list of numbers and outputs a list of numbers, right? Can I redefine add 5 in terms of map? Can I apply map to this list maybe?
Well, wouldn't you have like on that bottom row, like cons, X and S's?
So I would, but do I need a case split here? I'm using map now.
Oh,
So if I want to apply map, I could write, so, and let's make the holes a little bit more specific. I'm asking you to basically say, I want you to use map to write this function now. And this hole is expecting some A to B. Okay, but we know what A and B are going to be. We know that this is going to be a nat to nat function because of the input and output type of the lists. And then we'll give it the list X's. Okay, so what goes inside that other hole? Someone online might have been saying something.
That +5 function we did.
Yeah, so we could put +5 inside there, right? So here I can just do +5. Now, why does +5 look kind of weird here? Normally, how many arguments do I give +5? 2, right? I give it 2. But here I only give it 1. What do we call that? When we don't give all the arguments to a function.
The partial.
Partial application, right? So we've partially applied the function. This is the exact use case for partial application, where we don't actually need to give it all the arguments, because this is all we need. We just need a function, and we can get a function on 2 arguments by giving it one of the arguments, right? So now this is a function that requires 1 more argument. Okay, and that's what map calls for. That's what map needs, is just function on 1 argument. Okay. As a matter of form, we could also have left off the x's and the x's here. We'll actually look at that on the next example. There's a fun reason why that's true. So now how about all not? Closer. So all not had a similar type. List of bool to list of bool. Okay, and now I'm going to leave it as the most general case here. I'm not going to introduce any arguments this time. So now I want to apply map again. In this hole, I'm expecting the whole big hole before we do anything. In the most general case, I'm expecting a list of bool to list of bool. Okay. Now, what can fill that hole? Well, if we look up at the definition of map up here, it outputs a list of bool to list of bool if I give it something that's a bool to bool function. So how could I define all not this time? I kind of told you a second ago, but what could I put here? Or at least somebody get me started.
Map.
Yeah, so we can put map here. And then map now expects a function here from bool to bool. What do I give that? We have a function from bool to bool that does what we need it to do.
It's the not function.
Yeah, just not. Yeah, Linnea says just that. So we could just throw a not in there. Now, why did I write it like this? Why didn't I have, say, put an x's here and an x's there? I could have. It's the same function. Typically, as a matter of kind of keeping things clean, if we have x's there and another x's on the outside, we can use partial application here, just like anywhere else, because we expect a list of b to list of b function. And map produces, if I give it a function from b to b here, it will give me a function from list of b to list of b. Okay, so I can actually just leave that off if I want. You don't have to. You certainly don't have to. It's just a convenience thing. It makes your code a little neater. But this is another equally convenient way of writing this. And if you think about it, all not is a map. It's a mapping of not. So it's a little bit more of a concise definition. It's a little bit more readable. So just know that you can kind of drop it if they occur on that kind of farthest right side, respectively. Now you can't always do that. If I flipped the order arguments, that wouldn't quite work. But here this does. Questions on that part? Do we kind of understand what's going on with map? Any like uncertainty on why you would use this? Pretty straightforward functions. Do we think we could think of any other map-like functions?
Yeah, maybe if you had like I guess a list of strings and you wanted to count each string's length,
Oh, count the string's length?
at each iteration, essentially.
Oh, okay.
There's it on the string data type. So
Can you do that with a map? You can't do that with a map, interestingly enough. But you're on to something. You're on to something that we'll actually maybe come back to, because that was the third function I want to talk about today. So the function I'm thinking of, to pseudo, can we do multiplication? Not really. Multiplication doesn't really work here because that's just on numbers. But we could apply multiplication on each thing in a list. We certainly could do that. So we could use multiply everything by 2. But what I'm getting at is more, have we seen a pattern in functions? And maybe this is a harder question to ask, because I'm actually asking about a pretty abstract version. Yeah, I'm thinking about how I want to present this. Yeah, no, I think I'll actually just kind of lecture this part. So we have other functions, higher order functions on lists that we typically see. So there are 3 of them that we typically see anytime you're programming with lists. These are the kind of the big 3. And these functions are called map, filter, and fold. Okay, we've already talked about maps. Let's talk about filter. We'll get to fold at the end. What if I want to filter out certain functions kind of based on if they meet some kind of if check, right? Some if then else or some predicate, right? So remember and for those of you that don't know, a predicate is a function of type a arrow Boolean. Okay, so it's basically checks, like different checks you would run. So like, are these numbers less than 5? Right? Or the Booleans don't really work here exactly. Or say if I have a list of lists, or say if I had a list, is the length of this list less than 5? Or is the length of this list equal to something? Equality is one of these sorts of functions, kind of. So let's pretend we have an equality function. Or actually, let's not even pretend, I'll just write it. So like, let's write an equality function called equals for, say, the numbers, okay? This will take 2 numbers as arguments. And will give me a Boolean back saying if they're equal or not. Okay, and I'll just write this one out this time. So equals, if I have 0 and 0, then I have true. They are equal. Equals on S of X and 0 is equal to false. equals on 0 and s of y is also false. And then in the last case, if I have equals of s of x, s of y, I do a recurrence and say, okay, well, if they're equal if x and y are equal. Does that square with everyone's intuition for how equality works? Hopefully nothing too crazy going on here. Should be fairly intuitive, this example. Or this isn't even an example, this is just lead up. So now could I write a function that uses equals and filters out everything that's not equal to 5 in the list? So for instance, I write function with the following behavior. Okay, and so let's say we'll call this function all 5 or all 5s. Maybe we'll put an S at the end. All 5s on the list 5, 3, 5, 0 is 5, 5. All 5s on something like, let's say 1, 2, 3 is the empty list. I think you get the idea here. Try and write this function. You guys are definitely capable of writing this one on your own. Let's do that as an exercise, just in practice. Give you guys a few minutes to work on that. Remember to start by giving it a type. That's going to be your thing to start off with.
Professor. Hello.
Yeah.
Can I just see before this page a little bit? I miss.
Oh, yeah.
Sorry.
That's okay. Is that good?
A little bit further. Sorry.
Can go. That's about as far as I can go, or we lose the examples.
Okay. Sorry. I just want.
Oh, you cut out there.
That's good. That's good. That's actually perfect.
Okay.
Thank you.
Cool.
Thank you.
Okay, no worries. Ooh, I've just realized we're missing syntax to actually write this function, I think. Have we?
Kind of non-Boolean with
Yeah.
like a question mark.
Uh-huh.
Derivatives, what I call them. Or is it question mark in the
A
line?
ternary operator. We do need something like that. We do need something like that. So here we're going to use the a case statement in this problem, kind of like how you did on the homework, which you're allowed to do in the way we've been writing functions. You can still write case statements on the same line. So think about how you might use one of those to write this function. Because I just realized you do need to do a little bit more than we have. Yeah, Joseph, that's the right idea. Keep playing with that. But how do you check if something's 5? That's the tricky part. It's checking if something's 5. And I guess actually you don't need to necessarily do anything fancy with case statements. You could pattern match on the element of the list, but then you wouldn't be using equals. So try and use equals here. Oh, Linnea, that's the function we wrote right up above, just right here. Try and use that function to write this function. This might be a little tough for us to do, so we won't spend too much time on it. Yeah, Arthur, so we're filtering out everything. So we're not outputting a list of Booleans. We're outputting a list of numbers that meet the predicate, or that are equal to 5. That's kind of the tricky part. So let's talk about this, because there's a little bit of trickiness going on here that I only realized after I posed the question. So let's give this a type first. We shouldn't have had a problem with that. What type are we expecting here? Yeah, so list of nats, and it's a function, so list of nat to what? Another list of nat, right? Okay, and now what are our cases? Well, nil should be pretty easy, right? Nil's still going to be nil. And all 5s of cons x x's. This is the one where we're going to get stuck, right? What do we do here? So we kind of need to do two things. We need to check for equality and then also then pose an output. But that check for equality has to happen first. So I think the Scala notation, this is what we'll use in here. We would do a match statement, right? If you're kind of programming this in Scala. Yeah, so Joseph, you're about right there, but not quite. Instead, what we'll do is we'll actually match on the output of the equals function. So here we'll have equals 5 and x. Okay, put that in parens to make it all look nice. And then we have match. Okay, and now we can split this into multiple cases. I'm gonna clean this up a little bit. And I think in Scala, they like you to put a curly brace here. I don't really care if you do or not. Now, what are my cases? If I matched on equals, what are my possible cases now?
true and false.
Yeah, it's just true and false. So I have case true, case false. And what should these end up being? I guess if it's true, then we have x equals 5, and then what should my output be?
Cons x and then all fives x's.
Cons x, all 5s x's. I like it. I like it. Okay, so then we keep it around, right? We slap it back on the front and then do a recursive call. Now, how about the other case? And I think we already have it. From chat, it's all 5 x's for the second one. So if they're not equal, then we kind of throw x away, right? And we keep everything else around. And so I guess to point out here, we've done a couple new things. Actually, just one really big new thing is in order to basically apply a function and then also match on it, we used a match statement inside of a definition. We're allowed to do that, okay? In Scala, this is a little bit easier to write because it doesn't kind of play with both notations. There's another way we could have written this that's a little cleaner in the style we're used to, but we're not going to go that way. So this is kind of the new stuff. Is that highlight? That's a little offensive. I don't like that. That's a good highlighting color for green. Is blue good? Yeah, blue works okay. Yeah, so this is all kind of new, using a match statement inside of a function. We're allowed to do that. Okay, so it's a good handy tool to have in your pocket if you need to kind of do a check and then match on that check. You're allowed to do that. Yeah, so this captures that notion of all 5s, but let's imagine I wanted to do something like all 6s or all 7s, right? So there's a class of functions where maybe we're comparing numbers. What if I wanted all the numbers that were greater than or equal to something? So I'm just going to pause it. We have a function now called, actually here we'll use less than or equal to. And it takes 2 numbers. And outputs a bool. I'm not going to define this mostly because I think it's a homework problem. And I need to double check. If not, a homework problem is probably in a recitation, so I don't want to get ahead of myself. What if I wanted to use this in the same manner to filter things out? Could I abstract this? Okay. Yeah, and then someone in chat says you could slap a variable into this thing, right? So I could abstract and add a variable. Okay, so let's try and write something like filter, some kind of filter operation on lists. And what type should we expect? Okay, so let's call the function filter. Let's just leave the name kind of simple. I like that name. what are we abstracting over this time? Okay. Or rather, where are we, or actually, let's work from the other direction. All fives is a list of nat to list of nat. If it was, say, a list of strings, right? Say, keep around the strings of length 5 or more, or something like that. That abstracts, right? But what's the pattern here? We're taking a list, and what are we getting as output? Another list. And is that list the same type of list or a different type of list here?
But might could be different, you know.
Could it be different?
I guess if you wanted to make a list that was booleans, you know.
No, because that's actually, we actually already defined a function that can do that.
Okay.
So map can do that,
I
right?
see.
So map would actually, you could apply a predicate to a mapping. Yeah. So here we are going to leave the list the same. It's going to have the same output type. So I'm going to leave a little kind of space there, and then arrow list of A to list of A. But what goes on that far left-hand side? What goes over here? Yeah, so what could I put there instead? The word we just defined, actually. A little higher up.
Predicate in there.
We could put a predicate in there, right? What should our predicates type be? A to Boolean here. I guess I made it really easy for you guys. So A to bool, right? That is going to be a function, right? It's an argument that's a function. So filter is what? Filter's a higher order function, right? Because it takes another function as an argument, right? So these are really powerful functions. They do a lot for us. Before we start soapboxing about it, let's write this function, okay? Filter on, we'll call the predicate P, and we have X's. Yeah, X's. Do we need a case split here on anything? No. Interesting. Why not?
Is you're doing the like comparison of the predicate.
You're about there. So can I apply the predicate to anything here?
I guess you don't. Well, I think you don't need it because it's the other function's the one that's checking if it's nil.
Which other function?
Like your A to Boolean.
Is A a list?
You're right.
Yeah. So A is not necessarily a list, right? So should I be case matching here? Yeah, probably. So we'll case match on this part. Nil equals, and we'll have a case for cons per usual. Okay, what's my output for nil? Just nil again. Sad for nil. Nil is usually going to be output. Like usually when you're matching on a list and it's nil, usually it's still nil. It's boring, right? How about this other case, the cons case? I need to filter stuff out. So I need to check if it's worth filtering, right? If it hits the filter or not.
You're gonna have to have a match statement.
Yeah. So what do I give to the match statement? What am I matching against?
Predicate.
Predicate of a, here I give it a name now, X, right? Yeah. So P of X. So I'm checking if X satisfies P. And now I give the match statement. So right on, I like this. Okay, and what are my cases here?
false.
Yeah, true and false again. And what are my outputs going to be for this situation?
True's gonna be cons X, filter X's.
So cons X. Filter. Running out of room. P and X's. I ran out of room. So bear with me. I'm going to move this all over a little bit. P and X's. And then how about the next line? What goes for the false case?
Filter X's.
So filter PXs, right? Yeah, just wrong order. That's okay. Boom, and we've got a function, okay? Now we could rewrite all fives again. And this time we could write it as all fives is equal to filter of equals 5. Okay. That's our new definition of all fives, right? Really short. There's a pattern, so we can use that pattern, right? So good job writing filter. I don't think we'll do too many more examples with filter itself. I do want to ask though, so there's this pattern of checking a predicate, and then in the case it's true, we do something. In the case it's false, we do something. What do we normally call that? It's usually a built-in in your languages, if I'm thinking right. We check something. If it's true, we do one thing. If it's false, we do another. What do we normally call that in programming language? Yeah, so Arthur and John come in. It's an if statement, right? An if then else statement. So essentially, this piece right here is an example of an if then else statement. Can we abstract if then else into a function, do we think? It's a pattern. We saw it twice now, right? Where we match on some predicate and then spit it out. Do we write that function? I meant to write this last week, actually. We can write this function. So let's do that. This is usually, was this not on the homework or in the recitation? Weird. Well, it's not on, no, it's not on the homework. I feel like it should have been on the recitation. I'll need to update that for the future. So can we write an if then else function? What should the type of an if then else be? It's kind of a weird thought. You don't usually think about that, do you? What should the input be? Well, let's look up here. What's this? The P of X part. What type does that have? It's a Boolean, right? It's just a Boolean, actually, because it's P of X. We've applied it. So if then else takes a Boolean, arrow, and then what are its outputs? Yeah. Sort of, yeah. So there's some variability there. Could output anything. So we could use a what there. Use a variable for the type. Yeah, so we don't need to actually lock ourselves down to a type yet. So I'll actually give this one, this is kind of a trickier type annotation this time. So we have a Boolean as the input, right? So check this, okay. Here's the thing I want you to check. If it's this, then I'm gonna give it an A. That's the true part. If it's true, I'm gonna output A. If it's false, I'm gonna output that A. And the output of this function is an A. Okay, there's a lot of type variables there, but it'll make more sense in a second, I promise. So now if then else, we'll match on true and false. Okay, and then we have some other arguments to this function. Okay, what should we call them? So we have two A's that we're also giving this function. What could we call those? What would a handy name? We could call them X and Y, but there's probably a better name. Let's call them T and F. Okay. These have type A. We don't know what they are. They're not Booleans. They're just called T and F. So now in the true case, what am I going to output? What am I going to output?
Well, would you output T?
I'd output T, right? The naming kind of gives it away. And how about for the false case? F, right? Okay, that's why the naming of this makes sense, right? Just T or F. Now, could I use this to write filter again? Like rewrite that second case in filter? So let's copy it down. And try and rewrite it using if then else. And it'll be a much cleaner definition at the end of the day. Can I replace this part with that? Where I use an if then else on the front. Okay, so the if then else gonna have some holes. So there's a Boolean to start off. And then we know what the A's are because of the type. So it's expecting a list of A for the true case and another list of A for the false case. But here lists, oh yeah, list of A is fine. So what can I fill that in with? Yeah, so we can put P of X for the Boolean. Now, how about for the list of A for the true case? Yeah, right. So cons X filter PXs. So we have and the other case. I'll put it on the next line. Yeah, just filter PXs here. So same thing. It's just a little bit. I like this way of writing. It's a little cleaner. And you can break these out onto multiple lines if you need to. Spacing actually, fortunately, doesn't matter a whole lot. If you couldn't tell in Scala and in the way we write in class, more space doesn't really mean anything. It's not like Python where that matters. P3, what do you mean P question mark? Where were you trying to, where's P defined? So P is an argument to filter. That's right here. It's the predicate that we're passing in. Or that Boolean check, we're saying, okay, give me an A and I'll tell you if A meets some property. So it could be in like greater than or equals to, or for like a string, does it have length 5? You know, and any question you could ask of something in a list here. So yes, it's implied to be a function based off the type. So if we look right here, it's a type of A to Boolean. That's that. That where it's implied to be a function. It's not really implied even. We assert that it's a function. So it's a fairly strong statement. We're saying for sure this thing's a function. Questions about filter or anything else we've gone over? We don't. Oh, say that again.
Yeah, could you just say like I'm trying to wrap my head around like where you got a function there and then the arrow that points to list A and the arrow that points to list A. In plain English, what is the story those arrows are telling? Like we have a function that produces a list that produces another list, or
Yeah,
what
so,
exactly is that?
Sure. So I'm gonna start by actually doing some highlighting here. So this white corresponds to P. And then the second, or this first list, I'll use orange here, corresponds to this part of the function. And then the output corresponds to the right-hand side, or the output of the function, generally. So whenever we have an arrow inside parentheses, it's going to be a function as an argument. Or I guess I could write instead. Right? Normally, and this is kind of, if we think about our math classes about associativity, so we talk about things being right or left associative. Most of the stuff you've seen before, like addition, is left associative. So if I wrote something like 1 + 2 + 3, you would group the 1 and the 2 first. You don't do that with functions precisely for this reason. It's right associative. So we group these together first and then these together, if that makes more sense. And that might make some sense to some people and not others, so, and that's okay. When we add parentheses explicitly, that's usually going to indicate we have a higher order function at play. Because if I erase the green parentheses here, I'd just have A and B as arguments. And I don't want that because the B here is an output of a function, right? It's a little bit different than an input. Well, it's just not an input, right? Saying I need a function as an input. Does that clear that up? Or can you refine the question maybe if I didn't quite do it?
I was understanding you up to the point where you were talking about it being right associative, and that was making me think about like the way inputs are processed in a list-based language or something,
Okay.
where we resolve the innermost elements and work to the outermost elements. Is that what you're saying here?
Resolve to the outermost. It's related, but not quite in an intuitive way. So I don't want to go down that rabbit hole.
Okay.
Yeah, it's not quite the same. It's similar in that lists are, you'll typically see this kind of hierarchical association with the parentheses, but in I think, are you talking about Lisp?
Yeah, Lisp or Tickle or something like that.
Yeah, something like that. You always add the parentheses explicitly. Here, we kind of, when we're talking about function types, we don't always put them in, we just leave them off. These purple ones are usually not there. So typically, now I'm erasing too much, so I'm just gonna leave them there. This tells us how to think about the grouping of everything. So adding the parentheses, I guess, the kind of peel it all back, the parentheses here actually tell us something. We can't forget them and have the same information. It actually changes the meaning of the type to be a function as an input. However, when you put parentheses on the right side and associate things on the right-hand side, it actually just means input and output of a function. So here, it means we have, okay, so we read this arrow, it says we output a function from list of A to list of A. That's the correct reading. With or without parentheses, that would be true. But if I removed these parentheses, it would actually change the meaning of the type. It would be a function from A to B to list of A to list of A, instead of having a function as the input.
Okay,
I
yeah,
think-
that
Yeah,
makes-
and oh, was that better?
yeah, I think that might have cleared it up.
Okay, and as you guys get more practice with kind of actually using these, it'll become really clear. And fortunately, in Scala, this ambiguity in notation isn't quite as present. They get around it with some of their syntax. It's a really cool notation. It works really well, actually, once you get used to it, but it does take some getting used to. And hopefully those highlightings kind of help spell stuff out a little bit more too. Any other questions? Cool. Well, we don't quite have enough time to jump into folds today, so we'll pick up there on Tuesday. We're quite a bit ahead of where I'd like to be, so we're doing really good. Otherwise, I'll stick around for a few minutes if anybody has any questions. I don't have a ton of time today, but a couple of questions I can answer. Otherwise, have a good weekend. Be on the lookout for homework tomorrow. I'll post today's quiz tomorrow morning and give you guys a little extra time to do that one. Otherwise, have a great weekend, and I'll see you guys on Tuesday.
Thank you.
Thank
No
you.
problem. Have a good one, guys.